So giant covalents or something called network covalents. So maybe say this to the lab. That will help because you'll do just what we just did with glue.
But not it's yeah. Anyway, now you positive ions surrounded by a single sodium. Put that over there. Sodium. Yes, sodium. Bring that over there, positive surrounded by a single. Yeah. Repeating greenish structure with strong bonds. That's is there another one? Is there another one? Read your thing again. Is there another one? High melting point, always solid and high melting point. High melting points also. Hey, what's up, guys? Hey, what's up? I believe this is simple. Because you got hydrogen atom shit. That's simple. Covalent, yes. This is simple for sure. This one. I'll say this is
All right, and you have 10 seconds to make some final choices.
one of these is metallic. I remember metallic is just a flat structure. I'm gonna say this is giant covalent. And this is giant covalent. I'm gonna say that's giant covalent.
All right, pause. 3, 2, 1. Everybody, let's start with ionic, and we're doing this one more time. Ionic. Property.
Strong bond between atoms of chemical sharing.
Revise. But sharing is not a good word for ionic, right? Like if I give you a cookie, I know you're like, yeah, that's sharing. But that's really, I give him a transfer one. So Brandon's group, correct that. Oh, can I get some feedback? We're doing ionic right now, guys. I need that characteristic about ionic. Huh? Sure, do a new one. Yes, regular 3D arrangement. You guys make sure that you're focusing and fixing the okay. So regular 3D arrangement, positive and negative. I'll come back to you guys group. Bradley.
Said
all salts, think sodium chloride salt is a solid at room temperature. Always. Sodium chloride is our example there. Next, up here. What's your picture look like? Can you describe it? Thank you. Negatives and positives, ion hydrogens, and then this group right here. Okay, and moving on. Let's go to metallic next. Sophie's group. Malleable, great. Keep going. Kieran.
The game looks like a bunch of positives and then all next to each other.
And then those little tiny dots. Those dots are delocalized electrons. Okay. Keep going, Zach's group. Backtrack. Anything else? Yes, Nevsky, absolutely. Go on, going through.
Positive ions surrounded by a state of
Delocalized. Very good. Back to you guys. Caleb. Not the always one. The always one goes in ionic. This one says almost. All are solid. Brandon, what's the one that's not solid room temperature? Mercury, thank you. Jacob's group. And we already said conductivity. Beautiful, thank you. Avery. Sodium is an example of the metal. Ishmael. Metallic. Those are metallic. Malleable, we already said it. You guys gotta work with me. I'll come back to you, John. Yes, ions and delocalized electrons. Last one is regular crystal arrangement. Good job, guys. Keep going. Simple covalent. Back to you guys, Ishmael. Simple covalent. Right. Most don't conduct electricity. Actually, but that's graphite. The graphite one goes under a giant covalent. So actually, just put don't conduct electricity. So don't conduct electricity, period, goes covalent. Meredith group. Good job, Frank.
Strong bonds between atoms, electrons are shared.
Great. Iodine is an example of that. Ansley? No, that's the rest of you said there's a giant to it. We'll get into that in a second, okay? There's only two more here. Something about forces. Sophie's group? Good. Isolated molecules being forces. The forces are those. What's your picture look like? Show me. Carbon with the hydrogen around it. That's methane. That's calcar, basically. All right. Giant covalent. This is one that's related to something we'll talk about in a couple days. It's called network covalent. It acts really similar to covalent, but it has this really extreme property. So 3D structure with strong bonds between atoms. So 3D structure is what you're seeing on the picture. It's like a little building. You basically can tell it's being built in a 3D fashion. Strong bonds between atoms, electrons are shared, very similar to covalent, because that's what it is. It is still a covalent compound. Diamonds, think how diamonds are really, really strong. They have also really, really high melting points. Covalent structure, giant covalent structures are also always solid at room temperature, high melting points, and then most do not conduct electricity except for graphite. What would you assign graphite? Tinsel. And that is a giant network covalent solid. Use it daily. All right, back in the body. Let's get back to your desk. If you're taking a picture of it, do it now. I don't get back to your desk.
I'm paranoid when it comes to this.
All right, and if you have a laptop out, please halfway close to close all the way so I know that I have your undivided attention. And let's chat a little bit more. I might have to save my quiz for later. That took us a little longer than I intended, but that's okay. So to talk a little bit more about bonding and how the visualization kind of comes into play. You guys saw the gizmo stuff yesterday. You saw how the electrons were transferred. You saw how the atoms change size as they form ions. And so we described that a little differently. We actually draw something called a Lewis dot diagram, and I saw some of those on came around to see. Some like 25% done tables, some 125%. You guys did a fantastic job. You definitely need to finish up your tables because that's a great study aid. As you can see, it's compare, contrast, compare, contrast, compare, contrast a lot with those types of properties. So 2 questions I want to address now. What are the different shapes of covalent and ionic? And then what are some special traits of ionic and covalent? Discuss in your groups. You have 1 minute.
Ionic and covalent.
Yeah, the ionic.
I'm not really. Do you know how to shape?
I know ionic, but like no.
Yeah, you guys just saw some of your shapes.
I know.
And then
All right, back to me. 5, 4, 3, 2, 1. Ansley, what's an ionic structure look like? Well, you used a good word for that. A lattice structure. This is a lattice structure. This is, of course, a macro scale, a huge ionic structure. Positive, negative, positive, negative, positive, negative, and a nice 3D regular arrangement of a crystal. So a lattice is a way that we describe that. How is that different than covalent? Right, so it has an attached bond. Like, what's a molecule you drink every single day? H2O. Okay, so H2O looks like this. That's it. Bonded, and these are right here. These little dots are called lone pairs of electrons. It's a single molecule. That's a single one, but then I can draw it again over here. And there's another single one, but I'm not showing that regular arrangement of a crystalline lattice. So that's one way they're different. There are some special traits. Did anybody come up with a trait that we didn't mention in our warm-up activity? Special traits? Maybe put in your other category of your table? Nay? Okay, let me show you my special traits. Add this to your table, okay? If you have yours on your computer, pull it back up for me. If it's on a piece of paper, add it there as well. What's up? They were bonds they generally take on, yes. I'm going to do ionic first flow class with you guys. So these were some interesting features, which you already have most of this on your table. But the strength, and this is just a fact about ionic compounds, the strength of an ionic bond depends on its charges. So yesterday in your simulation, in your gizmo, you guys found that they acquire different charges based on the number of electrons they lost or gained. So look at aluminum. How many valence electrons does aluminum have? You should be looking at the periodic table at your desk or on the wall. Aluminum, 3, because it's in group 3. Okay, so I'm going to use this space over here. So aluminum has 3 valence electrons. How many electrons does chlorine have? 7, because it's in group 7. Okay, so chlorine has 7 valence electrons. So how many electrons does chlorine need to gain to be perfect? 1 more. What has to happen to aluminum? Has to lose how many? 3, because it doesn't want them. It'll drop back to its last octet, which was its 2s2 2p6. It'll drop back to a second energy level that's full. So how many chlorines do I need to allow for aluminum to do that? 3. So another chlorine with 7 valence electrons and another chlorine with 7 valence electrons. So this is what you guys did yesterday. They transferred 1, 2, 3. So what charge did aluminum have at the end? Positive what? 3 plus. And what charge did each of the chlorines have at the end? -1, because each of them separately gained 1, 1, 1. So Al3 plus, chlorine 1 minus. If I say something called charge product like in math means what? Multiply. Take those charges and multiply them. A +3 times a -1 equals, I'm just going to do absolute value, so it's just a 3. Okay, so that's a 3. How would that differ than like sodium chloride? Look at sodium. How many valence electrons does sodium have? 1. So how many electrons will it gain or lose? Say again? Just 1. So when it loses its 1 electron, what's its charge? +1. Okay. So if sodium is a +1 charge, and chlorine the same style will gain 1 electron. So +1 and -1. When you multiply those charges, what do you get? 1. So basically, you're looking at a charge product of 3 versus 1, which is a stronger charge, or which is a stronger attraction, the 3. So that's how I'm just giving you more information about how the strength of ionic bonds can differ. They're all very, 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 very strong, but comparatively, I would say aluminum chloride was stronger than sodium chloride, simply because of its charged product. And we'll dive into that a bit more as we go through the next couple of days. The word electrolytic you might want to add to your chart. Electrolytic simply means that it's able to conduct electricity in liquid phase, or aka molten phase, or aqueous. What's aqueous mean? Yes, dissolved in water, right, or in a solution of water. So you're adding these couple of terms to your chart, okay? So electrolytic just means that it's able to conduct electricity. All right, the other two terms that you might add to your covalent is information about, well, we kind of already said this already. If electrolytic means conducts electricity, what do you think non-electrolytic means? It doesn't conduct electricity. So I think we mainly use the phrasing versus that term, but that might be a good term to add to your chart. Volatile. Who knows what that word means? Say again? I like to use the word stable for like electron configuration so we don't get that confused. All right, everybody raise your hand. All right, who put deodorant on today? Higher. Okay, thank you. So, smell that? Oh gosh, it smells like cucumber melon. Yeah, okay, so why can you smell your deodorant? If it reacts with your body would start to like turn colors. Why do you smell your guys' deodorant? I think you started saying something. What do you say? I do that all the time.
Oh, it's because it has smell.
But why can you smell it? Like, how does smell work? Chemicals. Everything can be explained by chemicals. Give me more.
Neurons.
Okay, so the neurons are detecting chemicals, but how are the chemicals getting to your nose? They're floating from your underarm, come to your face, they go into your nostrils, and they bind with a receptor in your nostril. It sends a signal to your brain that says, this smells like blah, 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 because I've smelled this before, and my body is training myself to understand this smells like deodorant. So, but why is it coming off your body? It's because you got a hot body, and it's warming up your deodorant, and it's volatile, which means it's vaporizing very easily. So, if it's vaporizing really easily, it turns to gas like that, and the gas particles hit you in the nose, and then you smell good. Okay? That's also how stank works, too. But it's just because sweat and other BO is volatile. It vaporizes easily, hits you in the nose, and you smell it. Okay? Can you guys, smell your pencil? Nope. I don't smell anything. Is that volatile? No. It's probably more ionic than covalent, if anything, because of the bonding structures and the plastics here. It's not going to be volatile. You're not going to smell it. Okay, so I think that's good on the properties. There's a quick example of a lattice if you're looking for a diagram. I think many of you guys saw this on our little our practice, though. Stacked layers of the ionic lattice. And then our last part is going to be drawing Lewis dot structures. I'm going to put the lights on. Okay, what do you guys notice? Look at my periodic table. So dots are what?
Based off the group.
What do you mean based off the groups?
Like, groups would have a specific amount of electrons.
That's my phone. I have an alarm that says go to food line right now. I'm sorry. I don't know why that's on there. Interesting. Okay. So the dots are the same as the group, but you were saying what the group number meant?
There's valence electrons.
Valence electrons. Okay, so Lewis dot structures represent valence electrons as dots. Okay, so instead of writing out an electron, electron, electron all the time, we're going to draw those dots to indicate that these are able to react and even able to bond and so forth. So at this point, halfway close your computers because you're going to be writing down or drawing some of these for me. It's not going to be quite easily to type out a dot on your table charts, okay? So looking across the board, everybody in group 1 has how many valence electrons? 1. Everybody in group 8? Does everybody in group 8? Who doesn't? Helium. And so that's because it's really tiny, and it cannot take on more than 2 valence electrons because it's only got enough for 1 S2. Right, so hydrogen and helium are small. They only take up the first energy level, so that's why they only take on 2 valence electrons. Whereas everything else can go, you know, think about it, 1s2, 2s2, 2p6. Who am I talking about right now? Who's this? This is neon. Okay, so neon has how many valence electrons? And you can see that because 1, you can count to 8. Good job. And the 2s2 and the 2p6, there are 8 valence electrons there as well. So you should definitely see a connection to last unit. All right, so as a way to kind of use these in a pictorial diagram, let me show you this first. Show you the picture first. Look at sodium. Look at chlorine. What happened? So what's the word we use for? Transferred. Okay, so sodium transferred, and write this entire example out and label this ionic, okay? Sodium, Omar, go stand for the last vision. Thank you. So sodium has 1 valence electron. Chlorine has 7 valence electrons. What happened to sodium? It transferred 1 to chlorine. Right, thank you. And as it did that, sodium got a charge of 1 plus, which, remember, if it doesn't have a number after it, you assume it's 1. So it has a charge of 1 plus, and chlorine, which gained that extra negative charge, extra electron, now has a charge of 1 minus. So what we do is to indicate those valence electrons changing is we totally wipe out sodium, so we don't draw any dots around it at the end. But for chlorine, we put brackets there to say, these are all mine. These in this bracket are now chlorines because there's been 100% of a transfer. No question. Overall, chlorine has 8 valence electrons now. And so does sodium. They just backed up to its second energy level, which was full. So what do you think I mean by overall? This is neutral. Frank. Right, perfect. So our 2 charges will cancel each other out, equal 0, which is what we call overall neutral. So even though the ions are here and ions have charges, they complete each other, right? One offsets the other to create overall a neutral atom or a neutral ionic compound, despite there being charged particles within it. Okay? All right, so what you'll notice is that sodium now has octet inside, which was its last valence shell, and chlorine has kind of octet on the outside, which is its current valence shell. So this is an example of a Lewis dot diagram for an ionic compound. And so what do we do in the whole process, which you probably saw as I demonstrated? We write the symbol, we draw the dots for its valence electrons, draw the other symbol, draw its dots for its valence electrons, and then show the transfer. How did I show the transfer? With an arrow to show which one was donating and which one was gaining. And then at the end, we indicate the charges they've acquired. Give me a thumbs up if you're comfortable with that. All right, so basically that's everything for ionic at this point in time. We'll talk about the different parts of like the properties they correlate with as we do some more comparisons. And then let me make sure I'm to the page I want to go to. Oh yeah, let's draw one more. You guys draw magnesium oxide. MgO. Magnesium oxide. Do the same process. Yeah, you guys can talk about it. That's cool. and we're going to talk about that. Okay. All right, so what do you guys do with my magnesium and my oxygen? Magnesium lost 2 because it only had 2 valence electrons, which was less than 4, and this one had 6, so there's no way oxygen's going to lose that, right? So what happens? Transfer to oxygen, and you form Mg plus 2 charge and oxygen with octet around it and minus 2 charge. Overall, this charge is neutral because 2 plus and 2 negative make neutral. And then I know we want to probably write OMG, but we have to write MgO because you always write the cation first and the anion second when you're writing out ionic compounds. All right, remind me how electronegativity works with your hands. Which one's electronegativity? I see most of us doing this. Okay. Who's more electronegative? Magnesium or oxygen? So magnesium's like over here someplace, right? Oxygen's like way up here. So why is oxygen more electronegative? Do not say because it's forward, it's farther to the right and up. One less shell, so increases the, okay, so higher Zeph, which is better attraction between the nucleus and the valence shell. Okay, that's gonna stop there. That's great. Magnesium's got basically lower nuclear effective charge, doesn't attract the valence shell as much, and it's willing to lose electrons much easier due to some other factors. So, why does that make sense then with that factor being true and then showing what's happening here? Yeah, go for it, Siri. I have one more for me.
Since it attracts electrons better, it has higher Zeph, then it means it's good. Easily take the electrons from magnesium.
Right, so this one has a higher electronegativity value, this one has a lower electronegativity value. So the one with the higher electronegativity value wins the electrons and they 100% transfer over. This one could care less about the electrons. But what if you had some things that were like similar in their electronegativity? What would they, instead of causing a transfer of electrons, they could possibly share. But what if one was just a little bit more electronegative than the other? Would they still share? I don't know. We'll see. Okay, let's do me a quick favor. You know, you guys have your comics and storylines due tomorrow, right? Yeah. I have an example for you, and I'm gonna have you guys read. Do not. I know this is on whiteboard. Do not write on this. I just copied this today. They're comics, and I want you guys to read in pairs. I'm gonna pass out like 3 to a table for now. 2 to you guys for now. You're gonna read, and if you want to scooch it, you guys can see this better. I'm going to tell you exactly what I want you to do. Give me 1 second. Let me give you this more. I have some books with more than enough copies. I have some with less. So this is called, listen up, polar bear and penguin reading, okay? If you cannot see a comic strip, you need to scooch next to somebody that actually has one. Everybody's going to turn to the page that says Polar or Bear Essentials of Polarity. Okay, some of you guys have that copy like 2 pages back, so thank you for dealing with that nonsense. So read with a partner and complete the questions at the end. The questions at the end are copied on the front of some of y'all's, but you'll see the questions there. Now, do not write in this package. You guys will write someplace else in your notes. But as you read, discuss and or write down at least 8 things that you see that are relevant. Okay? So I'm going to give you guys about 10 minutes right now. Read and answer questions. You need to sit next to somebody so you guys can see those. And this is like the best way to talk about polarity before we actually jump in together.
With like the shielding effect, since like we're doing for magnesium and oxygen, and magnesium has like 1 shell, so it's like holding on to electrons.
Yes, it's holding on to it. Actually, but no, it has 1, 2, 3 shells.
Oh, you go off the
yeah. So it's 1. So it's 1 is 2, 2 is 2, 2 plus 6, 3 is 2. So it's 3 things. There's 6 shells. This one has 2 shells.
Oh, okay.
You can.
Yeah, I thought it was off the group. I guess that's because
Wait, would that be because there are more protons?
So they attract more electrons. So the temperatures and electrons in the electronegativity of the electronegativity tends to rise and fall as we move southwards. Rising of these isomers to further things.
Yeah, it should be like a helium.
Oh. Nobody has important to form, right? Calling insulin activity value zero because they're relatively non-reactive. When two So that would be interior molecule isn't what an interior isn't dipole. It's not a pole. And it doesn't spin dipoles. Hold on. Okay, so that happens to be So I think here's the fact where you have to be over. So
Well, that's really good.
yeah. So I want to special. Some people they have to so they're poor.
Right, yeah.
But
So like, alright, I was gonna say, cause like, carbon is the Russian acid bond itself. So to the point where it can bond all the way to without having to non-double. So I guess that's why.
and it was saying, yeah. I was saying,
All right, guys, make sure you're looking at the questions now. Raise your hand if you've already done 2 questions. Okay, see where we are. I can pull the questions here.
Meredith, you can see this up here. To actually answer the questions, right? To look at the.
let's answer some of these together. Because in the interest of time, I have about 30 minutes left with you guys, and I feel like maybe not quite that long. You're going to want some more practice time with me. So who, raise your hand if you finished the read, the comic read. Okay, so we're just going to keep working through that while we answer some questions. So here we go. We're not multitasking, but I want you to flip through your book as we go to look for the information that's here. So how does the book define a polar molecule? And I can't write on the board with this. Actually, I'll try, but how does it define a polar molecule? Will? Okay, so a difference in electrical charge across the molecule. Okay, and they indicated that by like a molecule like this one with the side of a partial positive and a partial negative. So that's a lowercase sigma. It's like I'm almost doing an 8, but I'm stopping. That's called partial. Okay. Define electronegativity. Meredith. Okay, I am abbreviating. Okay, so ability of a nucleus to attract electrons in a bonding situation. All right, and so we saw that difference in how the partial charges appeared and maybe didn't appear in some of those examples. Interpret the picture at the bottom of page 1. Explain how the iceberg, penguins, and polar bears represent trends in electronegativity. Who's got me here? Yes, Sandra.
Polar bears have high electronegativity because they're young and they attract electrons. And then the penguins have low electronegativity because they're more delicate.
Okay, so the penguins were kind of representing the metallic side of the periodic table. The iceberg was the periodic table, and then your polar bears were high in electronegativity due to the fact they were nonmetals, meaning higher electronegativity across the board. All right, what is the artist trying to portray? Let's see if this travels with me. You got it, computer? No. Okay. What is the artist trying to portray when there are two polar bears wrestling? Sydney, what do you think? The two polar bears, what page was that on? Maybe somebody at your table. Not the same charge. It's non-polar, but thank you, that's what I'm looking for. So we just talked about how electronegativity played into it, but if they're arm wrestling and they're equally fighting for the electrons, that means they have an equal pull from their electronegativity for their electrons, those zones that are in the middle of them that they're trying to share. Versus two penguins arm wrestling together, same situation, it's just a different atom, but they're still equally trying to share their electrons because they have equal electronegativity. Question 5, what are 3 types of bonds presented on page 3, and what happens with those electrons? So somebody from the front table right here, Jacob's table, give me one of them. Okay, so back to you guys. Bradley's group. Give me one of the types of bonds.
Non-polar covalent.
Non-polar covalent. Okay, and I want you all to write this information down because I'm going to go through notes with examples and not with the definitions. So that's what we're doing this kind of part together. So non-polar covalent bonds. How do their electrons? Give me some fact about their electrons. Ashton's table. What makes it non-polar? Okay, so either it's bonding between identical atoms or really similar electronegativity. Their atoms are the same in this case. Their electronegativity is very similar. So electronegativity and negativity being similar means that they equally share those electrons in the middle. And if they equally share the electrons, does one side of the bond have more electrons than the other side of the bond? Yay or nay? No. Equal sharing, that means that there's an electron here and there's an electron here and it's equally shared. Are there any partial charges, positive and negative, on this situation? No partial charges, right, because it's non-polar. So I think you're starting to see what polar maybe means. All right, one more from this group. Polar covalent, okay. And William, can you guys tell me what's happening with that type of bond?
So basically,
Not charges. Okay, so different electronegativity values still are sharing electrons, but how are they? Are they actually sharing them equally?
No, the one with the higher electronegativity is kind of
And it's unequal sharing. Okay, so it's kind of like if I have 2 cookies and I'm giving Omar, like he drops a cookie in the pile and I drop a cookie in the pile. We both gave a cookie to the pile. It makes sense for me to have one, him to have one. But if he's more electronegative than me, he's more greedy for the cookies. He would take his and then half of mine, and then he would have most of the cookies, and I would only have half. But we still shared. It's just we didn't share equally. And so that creates a situation where there was an unequal distribution of electrons. Unequal sharing does create a partial negative on one side and a partial positive on the other side. Not full of positives and not full of negatives though. So hopefully you're diagramming this a little bit for yourself as well. All right, and then that last type of bond, which I'll write on the board over here. Last type of bond, Frank's group back there. Ionic, right? And so we're like experts on ionic at this point, right? So we know how ionic looks. Ionic isn't a sharing at all, right? So what's the word we use for that? Transfer of electrons from one to the other. And in that case, how does the bond situation look? One side is totally positive. There's no partial nature to it all. It's a full-on positive. And one side is negative. But then, that's the one where the penguin's like running after it, right? The penguin's running after it. What's that indicating? What's that showing? They're attracted still. There's an attraction there between them because they're opposite charges attract. Electrostatic attraction is another way to say that. It's just our normal situation of how the magnetic kind of attraction correlates here. All right, so that's not too bad. Let's look at one more question here. Maybe. Okay, so why are there 4? Actually, let's look at a couple more. What do you guys think the 4 scoops of ice cream versus the 6 scoops of ice cream are representing for oxygen and nitrogen? Raise your hand when you feel okay with that. Yeah, Bradley.
I think it's the amount of, I was going to say amount of valence electrons, but I was...
Yeah, you're fine. Yeah, amount of valence electrons in the middle, right between them. So in the, what kind of bond is that? It's still covalent, right? So it could be polar covalent, it could be non-polar covalent. It does depend on the electronegativity of those atoms.
Non-polar?
So, well, it does depend. I don't know. Oh, this is oxygen. Yeah, so it would be non-polar. So this is 4 valence electrons that are being shared between the oxygen atoms. 6 scoops of ice cream, you can guess, is 6 valence electrons being shared between the 2 nitrogen atoms. And you can see that because they're showing it as scoops of ice cream, so we could draw those as dots. And we'll draw them another way in a couple minutes too. So I'm going to hold off on 8 through whatever at this point, because I think that you're seeing the difference in bond polarity and how that plays a role in maybe some characteristics of our molecules. So we're going to switch modes back to notes. So you can append this to whatever you were writing, but just push the comic to the side for now, okay? So know that you're with me. So draw this example for me under your polarity information. And I want you guys to talk in your group if it's going to be polar covalent or non-polar covalent.
I'll try.
Oh my goodness.
Draw your example out. No, I'm not.
college sometimes are peculiar, but no. So you guys can see, is there a transfer of electrons here? Yeah or nay? No, instead they just put them both in the middle and say, okay guys, we're going to share. We share them. You can draw it as two dots in the middle being shared like that. As you can see, both the chlorines kind of scooched together. I prefer to draw it as chlorine bonded, a line to chlorine, and then put the outside electrons as dots. So basically, I'm telling you a line represents how many electrons? Yes, so that line equals 2 electrons. So whenever you see that kind of from here on out, you're okay with that system of diagramming. So how many electrons are around this chlorine over here? 8. You're still considering the shared ones as a part of its kind of circle, okay? So there's 8, aka octet, right? Octet. And then how many, because they're sharing, you can double count these. How many around this chlorine? 8 again. But are there 16 electrons on this molecule? How many are there? 14. 2, 4, 6, 8, 10, 12, 14, but you double count the ones in the middle because they're technically around that chlorine atom each. Like a Venn diagram in this case. So that's the share. That's the common electrons. Thank you. All right, so why were they sharing? What was so special about their electronegativity? Same, so no one can pull one side to the other. And so is there going to be a dipole or an unequal sharing of electrons here? No dipole, right, so no dipole. That's kind of for your knowledge. They represented that in the reading. How about HCl? How would you draw HCl? How many valence electrons does H have? 1. How about chlorine? 7. 1, 2, 3, 4, 5, 6, 7. All right. Now, I just dropped a piece of paper on your desk. There should be like little half sheets. Now, this is an electronegativity chart. Please do not take these. These are my class sets, okay, guys? I have some extra copies. I'll drop these around. But this electronegativity chart has little tiny numbers on it. Look at the little tiny number beneath hydrogen. What does it say? 2.1. That's kind of giving you a scale, a magnitude of its strength of attraction for electrons. So write 2.1 En, electronegativity, underneath your hydrogen. Now what's it say for chlorine underneath there? 3.0. Is everybody seeing how to read this chart? Make sure you're looking on with a partner if you've not, okay? 3.0 electronegativity. All right, what's the difference, mathematical difference between 3.0 and 2.1? So 0.9, put electronegativity change, like difference. All right, so sometimes, yeah.
We have
2.2 on. So I've had, like the molar masses can change if you have different periodic tables, just a teeny tiny bit, like the atomic masses. Electronegativities can too. So I have like 3 versions of this, and they might vary by a point. So try to work with me, and I know that they might have a little difference there. Okay, so we can predict that this is going to be a covalent bond because it's a non-metal, right? Hydrogen's a non-metal, and chlorine's a non-metal. So we know that's going to be a covalent bond off the bat. But covalent has 2 varieties. Polar covalent, unequal sharing of electrons, and non-polar covalent, equal sharing of electrons. What was chlorine example? What was it representing? Polar or non-polar? Say loud and proud. Non-polar. Because it has a, say again? Okay, so I'm going to say basically no difference in their electronegativity values, so there was an equal sharing occurring between the 2 atoms. But then you look at hydrogen and chlorine, and you're like, whoa, 2.1 electronegativity, 3.0 electronegativity, we've got a difference in electronegativity. The difference is 0.9. There's a little guide on your periodic table here, and it tells you if the difference is between 0.039, it's what? Non-polar covalent. If it's greater than 4 or 0.4, and between 0.4 and 1.68, it's polar covalent. If it's like extremely large difference, it's going to be ionic. You guys see that? So that's going to be a guide that you'll use quite frequently. So we're going to write this out, put next to this polar covalent. Okay, that's for you to know. And just remember, you're going to look at that sheet. It's not memorized. You always get the sheet, always. But if you don't know how to use the sheet, that's on you.
All right, so how would I draw this once I cause my electrons to be shared? Well, first off, they have to be shared, right? So I have to draw them with an H bonded to a chlorine, because they're still bonding through covalent bond. Basically, these two electrons are going to go in the middle, which I've represented as a line. What's over here? So 1, 2, 3, 4, 5, 6. All right, so who has octet here? So, yeah, so around chlorine, there are 8 electrons, so that's octet. But look at hydrogen. How many does it have around it? 2. You still have to count those in the middle, right? So it has duet, as we call it. Why? Because hydrogen and helium are teeny, teeny, tiny, tiny. They cannot accommodate octet. They can only accommodate 2, as in duet. So we call it the octet rule, but it's kind of like a suggestion. It's not like a hard rule, okay? Yeah.
Why are we sharing?
Because it's a non-metal, non-metal, and non-metal, non-metals make covalent bonds. And covalent bonds need to share electrons. That's going to be in your chart, okay? Make sure you guys are having some of those kind of aha moments because you just saw this in your chart last night. So now we see this heavy influence of electrons over here and not so many over here. And what's really happening is that on this bond here, there's 1 electron and there's a second electron, right? Basically, these 2 electrons are just scooching towards the chlorine because it is what causes this just unequal sharing. Yeah, unequal share because chlorine is more electronegative. Not 100% transfer, but it's just scooching this way. So we're going to call this side over here partially negative, and this side over here, because it's lacking a full electron, it's going to be partially positive due to the lack of an electron, the lack of a negative charge. So draw your partial positive and partial negative on your chlorine and hydrogen accordingly. Give me a kind of get this. I need to kind of see where your questions are because this polarity stuff's a little bit more has some theoretical stuff behind it. It's like I'm almost gonna do an 8. It's like partial positive, partial negative. Okay. All right. I want you guys to try a couple of these. Looking at the electron or electronegativity sheet I gave you, you're going to consider these different bonds, okay? Oxygen with hydrogen, cesium with chlorine, chlorine with calcium, oxygen with bromine. Decide if it's polar covalent, non-polar covalent, or ionic. Write down these examples for yourself. First, start in your groups, and then I'll come around for questions.
So if it's ionic, it would be like a silver, and then if it's solar, so they have non-polar, it would be like
Yep. You need this electronegativity sheet.
how else do you
Okay. Okay.
Yeah, not too much.
That'll take 7.
So oxygen and hydrogen.
That's still
The hydrogen has 2, oxygen has 6.
But
So it was shared.
7. It won't form until it's not going to reach 8.
everyone has 1 and then partially has 6?
Yeah, so 7 are over.
It's supposed to be colder, right? Well, no, it was ionic.
You know what? Are we just finding the difference?
Yep. 5, 4, 3, 2, 1. So this is simple math. You're looking at the actual values, subtracting them to get a value that's positive. We're just looking for the main difference, absolute value. And I know you guys can subtract. So when you look at oxygen, hydrogen, you get 1.4 electronegativity difference. Classify that as a type of bond. Go. How do you know? Because it's between 0.4 and 1.69, right? So that is a polar, right? Polar covalent. So you know that you're talking about the bond. We're going to talk about polar molecules tomorrow. So polar covalent. So how does that look? When you draw this, you're going to draw oxygen bonded to hydrogen, but which one is more electronegative? Oxygen. So does it get the partial negative or partial positive? Because electronegative means it has a higher share of the electrons. Electrons are what in charge? Negative. So you can draw a partial negative like this and a partial positive like this to indicate that. Another way to indicate it is called a dipole moment, which you guys saw as an arrow on your little comic reading. You draw the arrow pointing towards the electronegative one. You put a little hash mark over here on the side. So that arrow thing is called a dipole moment. I hope that you're writing down some of these examples, because it's going to be hard to remember unless you're totally like photographic memory person. All right, so that's our oxygen to hydrogen. Looking at the electronegativity differences, we saw those polar covalent, and then we try to describe it in a pictorial manner. Same thing with cesium and chlorine. What do you guys say? Classify it. Say again? Ionic, right? Because it's a very large difference. 2.3? Heck yeah, so that's ionic for sure. How do I draw? Or what's true about an ionic situation? Do we have partial negatives and partial positives? No, we have like just full positives. So cesium versus chlorine. Who's getting those electrons? Chlorine, because it's more electronegative, 3.0. That's going to have a negative charge of 100%. And cesium likely lost that electron because it gave it up to chlorine. And so this has a full positive charge. And now we could actually draw Lewis dot diagrams with that, but I want you to see there's a full positive negative versus partial positive negatives because there's a shared situation up top. So similarly, we have a 2.0. So what do we have here? Ionic again. So who gets the electrons? Chlorine, because it is more electronegative. So I'm just going to draw this backwards in this case. Chlorine's going to get the full negative charge, where calcium gets the full positive. And there are a certain number of electrons they lose and gain. I'm just showing you generic stuff right now. Yeah.
You do draw the dots at the reaction.
Yeah, when you're drawing the actual Lewis dot structures out, but we're just looking for classifying bond types first. Ari?
So, in number 2, is cesium still after 1, or is it just doesn't like?
It gave up its 1. That's why it has a positive 1 charge, because it lost its 1 valence electron to chlorine. Yes, Brandon? Only because I wanted to show it along with this, but normally we write calcium first. Yes, sir. All right, so let's pause on this for a second. Look at your tables. Do you guys see the noble gases? Look at your little electronegativity chart. Okay, what kind of electronegativity do noble gases have? 0. Great. So they actually, most of those have 0. But helium doesn't have an electronegativity. Who else doesn't? Neon doesn't. Who else? Argon doesn't. But then we pick up at krypton, and does it have one?
Yeah.
Just slightly, right? What is it? Oh, 3.0, not slightly. Kind of a lot. All right, so these don't, because they already have octet, and they don't want any more electrons. However, krypton and neon, those things are huge. Those have like 3, 4, 5, 6 valence electron shells. They're huge. You can actually drop extra electrons in there, and they kind of don't even know it. So that's why they don't mind taking out extra electrons. If somebody needs to bond with them, they'll do it. So we're going to pause for a moment. I need to make some quick adjustments. 1 second. Tomorrow we're going to do a lab where we're building basically chemistry Legos. So building molecules to see how they form with each other and why they bond the way they do, and look at the bond polarity. But I don't think you're ready to draw them yet, because we haven't had a chance to draw them in class. So I'm going to tell you guys right now to only do the bond polarity stuff. And I'm going to demonstrate that for you guys now. Zach, what's your question? Which other ones on there? Yeah, so the transition metals, they bond a little differently than many other things. So I'm going to say they generally, they don't bond. or they bought entirely clean. We try to stray away from transitionals because they don't do a whole lot of normal stuff. Okay? So make sure everybody gets this. This is yours to write on. Please put your name on it right now. I'm going to demonstrate how you will think about electronegativity differences, and then we'll move on to drawing tomorrow. I think we get out at 8:37. Yeah. So you guys see the first example? It says CH3Cl. See that one? Okay. You are going to do the electronegativity difference between chlorine and hydrogen. Carbon and hydrogen. I said chlorine. Carbon and hydrogen, and then carbon and chlorine. I want you to do the electronegativity differences there. So if you would like to take a picture right now of my electronegativity chart, so you don't steal it from me, Steve, you also can find one online. It's under my website. I want you to try to do the electronegativity differences between the atoms that are involved in the bonding. You'll see them. All I want you to do, just electronegativity differences. Do not try to draw anything else on this chart. And this is your secret. No, these are my buckets. Yeah, whatever papers I left that are mine, please put in the buckets and I'll get them after class. Reading guides I'll take later. I wanted to see that you want them done today. Yes.
So you don't
I'm going to take it probably tomorrow because you saw all that stuff we're talking about right now. It's really relevant, so I think if you guys can read back versus reading your chapters, it's very nice. I think you did a good job with it.
Only this much.
Yeah. And I'm going to have to help you guys with that tomorrow. We didn't get far enough. That's fine. You're good. Guys, just try on electronegativity. We'll pick that up tomorrow.
Reading guide 7.
No, I wanted to use them for our bonding stuff today. We didn't get to it. What's up, Shelby? Oh, okay. What do you mean?